Good morning. So we will start with our next topic, that is elements with more than one valence electrons. We have already discussed elements with one valence electron, that is your alkali metals. There, in order to explain the spectrum or in order to explain the hyperfine structure of spectral lines, we have introduced a new quantum number J known as the inner quantum number. And with more than one valence electrons, that means as an example your alkaline earth metals, we have two valence electrons. That is the simplest case. Here, what will be the case that we have to discuss in this class? So when you have more than two valence electrons, you can assume that with the values L1 and L2, their quantum numbers, which quantum number, as you know, it is the orbital quantum number, with the spin quantum number, say S1 and S2. So in this case, we have to apply two coupling schemes. That means they are known as the LS coupling or the Russell Saunders coupling, and sometimes it is known as RS coupling, and also you have JJ coupling. So we can discuss them. So as we have discussed, you have two electrons, valence electrons, one with the orbital angular momentum L1 as well as spin S1, the second one with the L2 and S2, the corresponding values. Then there are two possibilities. That means your orbital, that means different orbital angular momenta may combine together to form a resultant orbital angular momentum. That means there is a combination of L1 and L2 vectorically to get a resultant L value. And also you know these L1 and L2 are vector. These vectors can combine in different ways. So this L has not a unique single value. It can have different values. And there are some methods for finding what are the different possible values. And also your S1 and S2 can combine vectorically to get different S values. And then this L and S, that means if there are so many possible values for L as well as S, one from L and other from S, they will combine to get a given J value as the sum of L and S. And this is known as the LS coupling, or as we have already named it as the Russell-Saunders coupling, or as the RS coupling. This is the first way of coupling. And you have another method. This L1 and S1, they can combine vectorically to give a corresponding J1 value, as well as your L2 and S2 can give J2 values. Then this J1 and J2, both are vectors, they can combine vectorically to get resultant J values. So here also you are getting a J value, and here also you are getting a J value. And this is known as the JJ coupling. That means the individual J vectors are coupling together to form a given J value. And here individual L vectors are combining to get an L. Similarly, S are combining to get the resultant S. That is why this is known as the LS coupling and this as the JJ coupling. So now we can look them in detail. And as an example, you can take L1 as 1, or you can take, say, L1 as 2, L2 as 1. And this is known to us for a single electron. We have always the S value as half. So L1 is equal to 2, L2 is equal to 1, S1 is equal to half, as well as S2 is equal to half. And for a given value, the actual value of your orbital quantum number, you are writing it as actually L star. And this you are normally writing as it is root of L into L plus 1 into S cross. This is known to us. So for this L1, what will be this L1 star? That you can calculate, and that value will be equal to root of 2 into 2 plus 1 into H cross, or in simple you can consider it as root 6. Similarly, L2 is equal to root 2. Not L2, you have to write it as L2 star. The case of S we can discuss later. So you have two vectors, L1 star as well as L2 star with the root 6 and root 2 units. So how they will combine? And according to our theory, this L1 and L2 will combine to give a resultant L value such that they can have values L1 plus L2 to next value you will write as L1 plus L2 minus 1, etc. up to L1 minus L2. And as you know, there is a possible 2L plus 1 values. So with L1 as 2 and L2 as 1, we can get them as L1 plus L2, the first value will be 2 plus 1, that is 3. Then L1 plus L2 minus 1, that is 2 plus 1 minus 1, that is 2. Up to the last value, this you can consider as up to this, the maximum value or the limit you have to take as L1 minus L2, and this value you are getting as 2 minus 1, that is 1. So this is the limit. So the possible values of L are 3, 2 and 1. So from this it is clear that the possible values of L star are root of 3 into 3 plus 1, that is root 12. This is root 6 as well as root 2. And I think we can represent this combination rhetorically as a figure like this. The three possible combinations are, this is L1 star, which you are considering as root 6, as well as you have L2, which is root 2. So this L1 plus L2 will give you capital L star, whose value is here root 2. We have already seen that the possible values of this L are root 12, root 6 and root 2. I will write the values here. L star can have values root 12, root 6 and root 2. So when they are combining like this, you will get the resultant values like this. And another one is like this. This is root 6. That means your L1 star. This is L2 star equal to root 2. And this is L star is equal to root 6.
Star.
This is L star, L2 star. And the third way, this is L1 star, which is root 6. L2 star equal to root 2. And this is capital L star, which is equal to root 12. So these are the only three possible combinations of L1 and L2. Means with L1 is equal to 2 and L2 is equal to 1, we are getting the resultant L values are 3, 2 and 1. And now about S values. With this S1 and S2, when you have two electrons, they can combine either or the orientation may be either in the same direction or in the opposite directions. That means there also you will be getting the values as from S1 plus S2 up to S2 minus S1 or S1 minus S2, whatever may be, you are taking the magnitude of that value. So here also you will be getting 2s plus 1 values. So here you can see that the possible values of S are either 0 or 1. That means half plus half as well as half minus half. So now you have 3 L values as well as 3 S values. Sorry, 2 S values. So one value from L and another value from S, they will combine to give a particular J value. So the possible J values are, J can be, the first one, L equals 3, S equals 0. You are getting this J as, here also, as we have already discussed, when L and S are combining, the possible values are from L plus S to L minus S. So here it will be L plus S is 3. Similarly, L minus S is also 3. So we will be getting only one value. And with L equals 2 and S equals 0, only one value. L equals 1 and S equals 0, this J can have value 1. Now, with L is equal to 3 and S is equal to 1, it can be from 3 plus 1, 4 to 3 minus 1, 2. That means your J can be 4, 3, 2. When L is equal to 2 and S equals 1, J can be L plus S, that means 2 plus 1 is 3 and 2 minus 1 is 1, so it is 3, 2, 1, and L with 1 and S with 1, J can be L plus S is 2, L minus S is 0, so it is 2, 1, 0. So the possible values of J, you are getting so many combinations. So from these, the possible combinations are 4, 3, 2 and 1. You are getting the final J values as either 4 or 3 or 2 and 1. So this method, you are calling it as the LS coupling. Here, individual L values combine vectorically to give resultant L values. Similarly, individual S values combine vectorically to give resultant S values. A possible values of resultant L are from L1 plus L2 to magnitude of L1 minus L2, and the resultant possible values of S are S1 plus S2 to magnitude of S1 minus S2. And it is normally found that this type of coupling occurs in lighter elements. That means here the interaction of orbital angular momenta is more than the interaction between your spin angular momenta and orbital angular momenta. That is why individual orbital angular momenta combine together as well as individual spin angular momenta combine together. So next we can look about this JJ coupling. So we can start with the same examples. We have L1 equals 2, S1 equals half, L2 equals 1, S2 equals half. So this will give you the first J value. That J1 you can write as, it is from L1 plus S1 to L1 minus S1. So L1 plus S1 will give you 2 plus half. 2 plus half, that means it is 5 by 2. And 2 minus half is 3 by 2. So you are getting only two values as 5 by 2 and 3 by 2. And here it is J2 as 3 by 2 and half. Now, combination from J and G. First you will consider J1 5 by 2 and J2 3 by 2. And as you know, the resultant value of J will be from J1 plus J2 to J1 minus J2. J1 plus J2 will give you, that is 4, and J1 minus J2 will give you 1. So the possible values are 4, 3, 2 and 1. With J1 equals 3 by 2 and J2 equals 3 by 2. You can get the possible J values as 3, 2, 1 and 0. That you can add. That means 3 by 2 plus 3 by 2 will give you value 3, as well as 3 by 2 minus 3 by 2 will give you 0. So the in between values 3, 2, 1 and 0. With the J1 equals 5 by 2 and J2 equals 1 by 2, we can get the possible values as the maximum value is 5 by 2 plus half, that will be 3, and similarly 5 by 2 minus half is 2, so it is 3 and 2, and with the final combination we can 3 by 2 and J2 is equal to half, it will be 2 and 1. So here also you can see that we are getting the values of J as 0, 1, 2, 3, 4. And that is an important point. So whatever may your combination, either LS coupling or JJ coupling, you are getting the same J values. The J values that you are getting is same. And we can't predict in a particular element which of these coupling scheme will happen. It is a general way of saying that in lighter elements the LS coupling dominate and in heavier elements JJ coupling dominate. And now a few words about the selection rules. So in the LS coupling we are saying that we can have the selection rule as delta L equal to plus or minus 1 and delta L as 0 plus or minus 1. And always the selection rule for delta S, as we know, it is equal to 0. And in the JJ coupling, actually we have no individual importance for L and S values in JJ coupling. So here you will say that delta J will be 0 plus or minus 1 and delta J can be 0 plus or minus 1. These are the selection rules. So this is the coupling scheme we have to discuss only. Then after this we have to mention about the space quantization that we can look in the next class. So have a nice day and we will be back with the next class. Thank you.